In this video, we're going to look at the parent functions of the trig graphs, and we're going to start with the graph of y equals sine of x, and then next we'll do y equals the cosine of x. So in order to graph these functions, we need to be able to think about what their values are on the unit circle. So remember that the sine is the y value on the unit circle, and I put some points on my unit circle here. I just did the quadrantal arcs because those are the nice ones to plot. So you can see if we started out at 0 degrees, the sine of 0, or 0 radians, would be 0. So my first point for my sine curve is going to be on the origin. I can also tell that if I went all the way around the whole circle, it would take 2 pi to complete that graph. So if I'm going to label my x-axis here, I want to be sure I go out to 2 pi, and then my quarter cycles would be at pi over 2, pi, and 3 pi over 2, because those are the 4 points that I marked in my quadrantal on the circle. I can see that my sine values vary between -1 and 1, so I'm going to put -1 and 1 on my y-axis. Now I'm going to plot some more points. So I started with the sine of 0 was 0, because that was my first spot on my unit circle. As my angle increases, when I get up to pi over 2, the sine is 1. So at pi over 2, the sine is at a peak. Then the sine starts coming back down. By the time I get to pi, the sine of pi is 0. Then the y values switch down and become negative. When I get to 3 pi over 2, the sine is -1. And as I get back up to 2 pi, my sine returns back to 0. So the sine makes a wave function. Its period, or the amount of time it takes to make a full cycle, is 2 pi, because that's how far it took to go around the unit circle and get all the possible values. Now let's do the same thing for cosine. The cosine is the x value of any coordinate on the unit circle because it's the adjacent over the hypotenuse. So you can see that my values for cosine on my x-axis, I'm going to have the same 4 quarter cycle points. My angles were pi over 2, pi, 3 pi over 2, and 2 pi. My maximum is going to be 1, and my minimum is going to be -1, just like it was for sine. The difference is, when I start at 0 radians, my cosine is 1, so cosine starts out up at a peak. As I move up towards pi over 2, my adjacent side gets shorter, so the cosine goes down to 0. As I move into the second quadrant, my cosine dips to the negative because I'm on the left, and by the time I get to pi, the cosine of pi is -1. Then I start increasing again and going back towards 0. By the time I get to 3 pi over 2, the cosine is 0. And by the time I get back up to 2 pi, my cosine is back to +1. So the cosine function also makes a wave. It's identical to the sine wave except for the start point. The start point for a cosine is at a peak, whereas the start point for sine was in the middle of a curl. So these are our parent functions, and we need to be able to make changes to them. The transformations that we're going to make on our sine and cosine curve are the same transformations we've made on all kinds of functions. When you multiply a number on the outside of a function, it stretches you vertically. That's what we call the amplitude. Now the amplitude is the height of a wave. So it's the distance from the middle of the wave to the peak, or from the middle of the wave to the valley. Since the amplitude is a length, we're going to say that the absolute value of a is equal to the amplitude because it's always positive. If a were negative, we still would have to flip our graph over, just like we did for any other function. We have another change that's on the outside of our function. If I think of this as being the sine, the b and the c are happening inside. Let's look at what else is happening outside. Outside, we could also add. When we add on the end of a function, it moves the function up and down. That's going to move our midline. We can also call this the sinusoidal axis, which I clearly can't spell, but the sinusoidal axis is another fancy name for the midline, and that would be y is equal to d, however much you move up or down. So if d is positive, it's going to move you up. If it's subtracted, it will move you down. B and C are inside of our sine curve, so those are going to affect us left and right. The b is going to affect the period. The normal period for a sine curve or cosine curve is 2 pi. Anything on the inside does the opposite of what it says, so rather than multiplying our period by b, the period will be 2 pi divided by b. The c is the value that I've added or subtracted inside. So c is what we call the phase shift. That's where we move our point left or right. When we describe a phase shift, we would like to say whether it moves left or right. Remember, if we're subtracting c, that's going to actually move us c to the right, whereas if we're adding a number c, that will move us c to the left, because everything on the inside does the opposite of what it says. Here's an example of a trig function, a sine, with all of the changes that we could possibly have. So let's look at what happens here. We have a 7 out in front of our trig. That tells us that the amplitude of our graph is going to be 7. Our other outside change is the +3 on the end. That tells us that our midline, or our sinusoidal axis, has been moved up to y equals 3. Before we can look at what's going on the inside, I would rather look at this in a different form. I need to have a phase shift occurring to only x. So I need to take this 4 and I need to factor it in front of the x. When I do that, I will be dividing the 4 out of the 3 pi over 4. Realize if I'm taking 3 pi over 4 and I'm dividing out 4, that's the same thing as taking 3 pi over 4 and multiplying it by 1/4. So essentially, whatever you're putting out in front, you're going to do the opposite to what was originally on the inside. When I do that, I get 3 pi over 16. That means I have 3 pi over 16 inside my parentheses. A lot of you struggle with factoring when it involves fractions, so it's a good idea to just double check once you think you've got your factors. If I redistribute, am I going to get the original problem back? In this case, if I redistribute, I would get a 4x. And then when I distribute the 4 to the 3 pi over 16, I would reduce out a 4, and I would get 3 pi over 4, which is what I wanted, so I know I factored correctly. So now I have a change with this 4 multiplied on the inside. Multiplying on the inside is going to shrink me horizontal. So my original period of a sine curve would have been 2 pi. Instead of multiplying it by 4, I'm actually going to take 1/4 of it, which gives me 2/4, or pi over 2 as my new period. The phase shift is what I've done on the end here. So my phase would be 3 pi over 16, and that's to the left. So that means when I'm graphing, if I were to put an x-axis up here, I know that my first point I'm going to graph is going to be at -3 pi over 16. When we graph, we like to graph for 2 complete cycles. If I'm doing 2 complete cycles, that means I need 9 points on my x-axis. I already have 1 tick mark, so I'm going to put 8 more on. 1, 2, 3, 4, 5, 6, 7, 8. I'm equally spacing them, but right now I'm not worrying about exactly where they go. That's the next thing I'm going to figure out. In order to figure out where they go, I need to determine how far do I go to the right to make the next mark. Well, I know I need to make a full up and down curl within 2 pi over 2, because that was the period. But where I make my marks, we're a quarter of the way each time. So I need to find what a quarter of a cycle is. A quarter of my period, which was pi over 2, would be pi over 8. So that tells me that every time to get to the next mark, I'm going to need to add pi over 8 to my previous value. If I'm starting at -3/16 and I'm trying to add pi over 8, I would like to have a common denominator to add my fractions. So my least common denominator would be 16. So I multiply, and instead of thinking of this as pi over 8 that I'm adding, I'm going to think of it like 2/16 that I'm adding. If I have -3/16 and I add 2/16, that gives me -1/16. Add another 2/16 is +1/16. Then 3/16, and 5/16, and 7/16, and 9/16, 11/16, and 13/16. By the way, if these reduce, I usually don't bother because I'm just going to have to get a new common denominator to add my pi over 8 or 2/16 again. So I have an x-axis. Let's draw a y-axis. You need to be sure we put our y-axis in the correct location. I have a negative x value and a positive x value, so my y-axis should be right in between those two. Now I need to make some marks on my y-axis. The middle of my y-axis needs to be at y equals 3. From there, I'm going to go an amplitude of 7, so I will go up 7 and down 7. So if I put on my midline of my graph right here at 3, and I think about going up 7 from there, that would make the height 10 for all of my peak points. I also need to go down 7. If I do 3 minus 7, that puts me at -4, and all of my valleys will be down there at -4. In order to make a nice smooth curve, I like to do some highlighter lines or a light pencil line to indicate where all of these heights were. Now I can tell I'm going to oscillate or flip back and forth between these 3 heights. So my first point was where my phase shift was. That was at pi over 16 to the left. Or sorry, 3 pi over 16 to the left. Remember, sine starts in the middle of a curl, so I should be on my midline right there. The parent function for sine started in the middle and then it went up, so my next mark on my axis was at negative pi over 16. I would be at a peak. I have my y-axis drawn here, but it wasn't one of my tick marks, so my next point needs to be over here at pi over 16, and at that point I'd be back in the middle again. Then my next mark would be at 3 pi over 16. I'd be at the bottom. Then I go back to the middle, up to the top, back to the middle, down to the bottom, and back to the middle. Now I need to connect my dots. My upward parts are bending down, and my downward parts are bending up. So I'm making my curve not too pointy, it's curvy. It would keep going forever in either direction, even though I've got points at the end. I'm going to put arrows there, and I can see that I have a nice smooth wave function. If I were writing the domain of this function, it would be all reals because it goes forever to the left and right. If I were writing the range of this function, I would need to say that it's sandwiched between -4 and +10. They're both going to get brackets because I equal those numbers. I could also write it in interval notation or in bracket notation, and I could say x is all real numbers for my x's, and for my y's I could say y is all reals, or I could leave that part off if I wanted to, but that -4 is less than or equal to y, which is less than or equal to 10. I would need to sandwich this in between because I'm both things, and make sure you put equal to parts of that. What if this had been a cosine instead? In the beginning, all of my work would have been the same. It would have had the same amplitude, period, midline, phase shift, quarter cycle. The difference comes when I go to draw my function. A cosine curve in the parent function started at a peak and went from there. So when I start my graph at -3 pi over 16, I would need to be up at the top. And my next point would go to the middle, and then to the bottom, back to the middle, up to the top. So the only real difference here when I'm graphing sine versus graphing cosine is just where I start my graph. I still start wherever the phase shift is, but for the cosine curve, where my phase shift was at a peak instead of a valley. The domain and range would still be exactly the same, and all my other information is the same as well.